Hello and welcome to another video. In this video we're going to be working on linked lists in a binary tree. And in this one you're given a binary tree root and a linked list head with the first node, and return true if all the elements in the linked list starting at the head correspond to some downward path connected in the binary tree. And so a downward path starts at some node and goes downwards, and you can't have any breaks. So for example, if the linked list was 4, 2, 3, this wouldn't work because we have 4, 2, and then like a gap. So this downward path has to be all in a row. So in this first example, the linked list is 4, 2, 8. So we have 4, 2, 8. So that is there. In the second example, it's 1, 4, 2, 6. So we have that one. And in the third example, there is no exact path that contains these things. So this is kind of similar to, like, you can imagine if you're looking for like a substring in a string, it's kind of similar. And what you have to realize is you can't just like do some greedy thing of like, let me go down the tree, and anytime I see maybe like maintain a pointer to my linked list, let's say my linked list is like, you know, this, you can't just be like, well, every time I go down here, I will just see if I see a node, and if I do, then I'll just like go to the next node and I'll try to find that, and so on and so on. Because there's a bunch of counterexamples, but let's take a look at a couple, or just one, I guess. So let's just say we have this. And so let's say our linked list is like, or our tree here is like 1, 1, 1, 4, for example. So essentially, let's say our linked list is like 1, 1, 4. And our strategy is just like, okay, maybe we'll just like we'll start here and we'll look for this first node, and once we find it, we'll look for the second node, and so on. So here we find the first node. So we have another pointer, and it can be like here, let's say. Let's make this bigger. Okay, so we find this node, and let's say like, okay, we find it. So now when we traverse down, we look for this node, and we find this node. And then when we traverse down, we look for this node, and we did find it. But we don't actually have, like, this is not that path. So for example, let's actually change this to a 2. So this wouldn't work because here you would find these two nodes, but then you go down here and you'd be like, okay, this doesn't match, and then you go here. So you actually, I think what you have to do in order to get the true matches is you actually have to start at a node, and then from that node you have to start at the start of the linked list, and then you have to traverse recursively. So what that would look like basically is we start a node and we say like, okay, from this node, are we able to match this exact linked list from this node? So we'd say like, okay, if these two nodes match, then let's check at the left and the right for the next node. So we'll check like this for this node. And if this is a match, then we'll check both of these for this node, and so on. And basically, like, you can think about it, the worst case scenario is going to be pretty bad here, because imagine if we have something like this. You know, let's say this is like 1, 1, 1, 1, 1. Okay, let's say our linked list here is actually this. So what would happen here is we'd have a match here, and then we'd have to like go left and look for this node, and we have a match again. So actually, so we don't really go left. So let me draw a couple more arrows to illustrate this better. So once we have a match here, we're going to recurse both left and right. And let's say we go left first. Once we have a match here, we're going to recurse both left and right. And then once we have a match here, we'll recurse both left and right. So we're basically going to be checking like this whole tree for this list. Even though this list is only 4 nodes, we actually end up checking this whole tree. And then we end up finding it at the very end. If our strategy is like recurse left and then recurse right. Hopefully this makes sense why. Because anytime you have a match, you have to recurse down both of the paths, left and right, for the node. So actually the time complexity here is when you start at a node, worst case scenario, you're going to keep branching at every branch, and it will be something like 2 to the length of the list. But luckily we don't have that many nodes in this tree, so I think this, so there's only 2,500 nodes in the tree, so we're limited to 2,500 nodes. But essentially, worst case, it's going to be like 2,500 times 2,500, because we can just keep branching and branching and branching. So if this linked list is like, you know, even something small like 10 ones and a 2, and this whole thing is made up of 1s with like a couple 2s at the bottom, you can see how you're going to start here and you're going to keep branching. But hopefully this makes sense why you can't do some greedy thing where you check for some number, because it has to all be in a row. So the basic idea is start at a node, then run function at that node comparing its value to the list head if match recurs to children. And so we just keep doing this. If match recurs to children, if match recurs to children, and then if any one of the children matches, you keep recursing and recursing and recursing. And then your final thing when you return true is when your node value matches the last node in the list and there's nothing else. So essentially you basically recurse to all the children, and if any one of the children returns true, in which case this one will return true, then we say it's true. Otherwise, if we weren't able to start here and do this whole thing, then we'll start at this node and do the same thing. And then we'll start at this node and do the same thing, and so on. So we have two functions. We have a traverse function, and we have a DFS function. And the traverse will just do a normal traversal, and the DFS will try to match, starting at this node, the entire linked list. So hopefully that makes sense, and that's kind of what we're going to do. And I think that's a tricky problem because you might look for like optimizations, and there aren't any. I think you can do some kind of string matching thing. There are things you could do because let's say it would be kind of tricky for a tree, but let's say your string is like A, B, A, B, A, B, A, B, A, B, something like this. And then like this. And you're matching with A, B, A, B. So the idea is basically like given this big string, try to see if this thing is in here. Same kind of thing as the tree. And basically what you do is you would start matching at the first letter, and you see like match, 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 match. Okay, there's no match here, so now I have to start at the second letter and do the same thing. Start at the third letter, start at the fourth letter, and so on. And there are string matching algorithms to make this faster, so this would be like n by m, kind of like this thing would be basically n squared. And there are things to make it faster, but it's kind of complicated, so I'm not going to go into those. But yeah, essentially this is basically going to be n times 2 to the m if m is the linked list, but this is also bounded by n, so this can't be any bigger than n. So it'll be something like min, like something like that will be the time complexity, and it'll still be fine. Okay, so that's what we're going to do. So we're going to have two functions, a traverse function and a DFS function, so let's code those. So the traverse is just going to be a standard traverse, so it'll just be list node cur, and all we're going to do is we're also going to pass in the head of the linked list. And all we're going to do is just check, we're going to call DFS on this node and say, given this node and the head of the linked list, can we have this whole linked list starting at this node? So if the head of the linked list is this node, can we have it? Like if we start here, then we start with the head of the linked list and we say, is there a path down that we can traverse? So basically we can say, I guess we can say if cur is null, or cur value does not equal head value, then we can just return false right away because obviously you can't do it. Otherwise, we're going to return DFS on, actually, let's think. No, I think we can just straight call DFS. Yeah, let's just straight call DFS and call DFS on the children. So if cur is null, return false. Otherwise, let's just call DFS on this node, starting at this node, and then we can handle everything else in our DFS. So we'll call DFS on cur and head. Okay, and that's all we need. Yeah, and then the next thing we need is the DFS function. So separating these out makes it a lot easier to write as well. So that's why. And this is just going to return a Boolean. So, oh yeah. I don't know why I did that. Boolean. Writing in too many languages lately. Okay. So, yeah, so we have this traverse and we have a DFS. So this is Boolean. This is Boolean as well. Okay, this is going to take a node. This is going to take a list node. It's not going to be the head. It's more like going to be like cur node or something. Okay. So if the current, actually, screw this up. So this needs to be a tree node. This needs to be a list node. Okay, so if the current node we're at is null, then there is no match. Otherwise, or cur value does not equal cur node value. So if there's no match, otherwise, if there is a match, let's also check for one more thing. So let's say we do have a match. Like let's say this matches some node in the list. We have to check, are we at the end of the list? If we are at the end of the list, then we made it, so we can just return true. So if not current node next, return true. Otherwise, we have to recurse down to the children. So recurse return DFS cur left, or actually, so cur left and cur node next, or DFS cur right, cur node next. And that way, if like one of these, like if you have these or returns, like if this works, it'll return before checking this one and so on. Because once we find a true value, we don't have to keep looking. So basically, if anything is true, if this is true, you know, if we ever have a match, we don't have to check anything else. We just check if we ever have a true value ever. Right, and then here, we just return the traverse function, and we pass in the root and the head. Okay, and I think like the head can't be null or anything, and the root can't be null. So if the root is null, it's fine. Okay, let's see. This needs to, we can't do this, so this needs to be does not equal null. Or actually, it equals null. Okay, so if we're done with linked list, return true. All right, there we go. Okay, we got an error, so let's just double check all this. So we traverse root with the head. Why do we have cur here? Oh, right. Yeah. Okay, so the thing we screwed up is we have to call DFS on the head, but we also have to call DFS on its children. So or DFS cur left head, or actually sorry, not DFS traverse on its children. So cur and we don't actually have to pass this because we're always going to call DFS with the, actually we need access to it. Okay, so we're going to call cur left with the head and traverse cur right with the head. And like I said, the idea is we can have these ors, and if any one of this is true, it won't execute the rest. Right, so in pretty much every language, if you have A or B or C, if one of them is true, it'll just stop. So it'd be faster. Okay, now we should be good, I think. Let's see. Okay, there we go. Yeah, so like I said, the time complexity here is going to be n times the minimum of 2 to the m, because like I said, we can split at every single path or the size of the tree. We can only check every node in the tree. We can't check anything more than that. Space. So let's see what we're doing here. So the traverse function is going to be recursive, and we can recurse down to, let's call it h, where h is the height of the tree. And the DFS function is also going to be recursive, and it can also go down to the height of the tree, I believe. So I think it's just going to be like this, something like that, right? Because no matter what node we start at, we're only going down. So we start at some node, and we're going to be traversing all the way down, and then no matter what node we start traversing at, we can only go down to h, which is the height of the tree. So I think something like this. And I guess let's see what happens if we get rid of this. Let's see what this thing says. N, H, yeah, same thing, I guess. Technically, yeah, if it's like a bad tree, then it will be N. So, yeah. So hopefully this is helpful. If it was, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.